So far, we have solved degree 2 recurrence relations. And so for Fibonacci, the characteristic equation had two distinct roots, and we saw an example where we had a repeated root. Now let's look at the general pattern. How do we solve general linear homogeneous recurrence relations of degree k? So let's say we have a general linear homogeneous recurrence relation of degree k. So it looks like this. An is going to be a combination of like C1 times AN minus 1, C2 times AN minus 2, all the way up to CK AN minus K. And so the characteristic equation is going to have degree K here, right, if we assume that the CK here is different than 0. So it's going to have degree K, and it's going to be written in this form. And this can have, let's say, T distinct roots. So we know that it's going to have K roots, but you can have repetitions, right? So let's say that it has T distinct roots. So these are the different roots with multiplicities. So again, the multiplicity is how many times the root is repeated. With multiplicities M1, M2, MT. So here we're saying that R1 is repeated M1 times, R2 is repeated M2 times, and so on. So then in that case, what the general solution is going to look like is in this form here. Now, this formula looks complicated, but the idea is simple. So the idea is that each root, so we're summing and we're going over all the roots, so each root appears once, and it contributes an Ri to the power of n. So each root is contributing with some R to the power of n. And the idea is that if the multiplicity is 1, so let's say that the root appears only 1, then this here is just going to be a polynomial of degree 0. So you see that the degree of the polynomial is the multiplicity minus 1. So it'll just be a constant. Now, if the multiplicity is 2, and we saw an example of that before, this is going to be a polynomial of degree 1. So it's going to be something of the form alpha plus alpha times n. Now, if this has a multiplicity 3, it'll be a polynomial of degree 2, so it's going to be some alpha 0, some alpha 1n, and alpha 2n squared, and so on. So the idea is that if a root appears more than once, then it contributes a polynomial in n times r to the n. So in other words, the multiplicity tells us the degree of the polynomial that appears in front. The constants are then determined by the initial conditions, and so you're just going to have to solve a big linear system. And so this is exactly what we saw in the repeated root example before, right, where we had to solve a linear system for that. And so let's see an example of how this looks like in general. So the idea is, imagine that you solved a problem where the characteristic equation had the following roots. So it had the root 2 repeated 3 times, it had the root 5 repeated 2 times, and the root 9 repeated only once. In other words, the distinct roots are 2, 5, and 9 with multiplicities 3, 2, and 1. Then the general solution, An, is going to take the form, you're going to have this term 2 to the n, and since this has multiplicity 3, you're going to have 3 parameters here, so this is going to be a polynomial of degree 2. You see it has 3 parameters. Now, since 5, so 5 again is a root, so it appears here, 5 to the n. Now, since it has multiplicity 2, you're going to get a polynomial of degree 1, which has 2 parameters. And 9, since it has multiplicity 1, you're just going to get a polynomial of degree 0, which is just a constant here. And so this is going to be your general form for An. And so then if they give you initial conditions, you will use those to solve a huge linear system to find alpha 0, alpha 1, alpha 2, beta 0, beta 1, and gamma. And then you'll find the solution to your problem.